Hi, I'm Professor Goins. In this video, I'm going to look at the idea of an osculating circle. The osculating circle is a way to visualize the curvature of a graph at a particular point. In particular, let's say I have this red curve right here, and I'm considering this point P on the curve. If I want to look at the best possible approximation of the graph by a circle, I could put this black circle in here, and again, it's the circle that best matches this curve, and we call this, again, that's the osculating circle. The center of that circle, we refer to it as the center of curvature. The radius of curvature is the radius of the circle. If I consider this graph right here, notice that I highlighted this point and this point. We can see that this part of the graph has a tighter curve. This part right here is more open. So larger curvature, notice that has a smaller radius. A larger radius means that the curvature is more open, so it's more flattened. And so what that tells me is that as the radius increases, then I know that the curvature decreases, right? So if I go from, say, this point to this point, I see that the radius increased, but the curvature decreased. Similarly, if I go in the other direction, as the radius decreases, that means that the curvature increases. And we can summarize that by saying that the radius and the curvature have some sort of an inverse relationship. As one gets bigger, the other one gets smaller. So the theorem, I'm just going to state this as follows. The curvature at a point is the reciprocal of the radius. Okay. So the curvature is the reciprocal of the radius. All right, so let's do an example for a fairly simple space curve. Let's find the equation of an osculating circle. So for example, let's look at the space curve r of t is given by t comma t squared. Right. Well, that's equivalent to the graph of y equals x squared. So this has the same shape as y equal to x squared. And let's find the osculating circle at the origin, or at the vertex. So find the equation of the osculating circle when t is equal to 0. All right, let me clean up the side of the board. All right, so remember that, here's solution. Remember the formula for the curvature of a space curve is given by the reciprocal of v. Remember, v is the derivative of r, and then multiplied by the derivative of the unit tangent vector. And then again, we'll evaluate that at the point when t is equal to 0. All right, so once again, for the vector function r is given by t squared. So therefore, the vector v is given by 1, 2t, right? Differentiate each component. The magnitude of v is the square root of 1 squared plus 2t squared, which would be the square root of 1 plus 4t squared. So that would be the magnitude of v. And then I need the unit tangent vector. Remember, the unit tangent vector is given by the normalized vector v. So the unit tangent vector is given by v over the length of v, or v over the magnitude of v, which would give me 1 over the square root of 1 plus 4t squared. And then the second component would be 2t over the square root of 1 plus 4t squared. So there's the unit tangent vector. And notice what we need to do is we need to take the derivative and then the magnitude of this. Okay, so the derivative of the unit tangent vector. So again, I'm going to need the derivative of each of these components. And for the first component here, we could rewrite that so that this is, instead of the 1 over a square root, we could write that as to the negative 1/2 power. So this would give me, let me just start by rewriting it before we differentiate. 1 plus 4t squared to the negative 1/2. And then for this one here, we'll just use the quotient rule, but I will write that as a 1/2 power. So 1 plus 4t squared to the 1/2 power. All right, let's go through and compute the derivative of that. All right, so the derivative of t, so dt dt. Derivative of the first component here, so this is going to be a chain rule. That's negative 1/2, 1 plus 4t squared to the negative 3 over 2, right? Power rule. Bring the exponent down, drop the exponent by 1, and then the derivative of the inside comes out as a factor, which would be 8t. And then derivative of this component, so that's going to give me a quotient rule. With a chain rule, of course, is going to be involved in there as well. But let's see, so the derivative of the second component, so the derivative of the top, which is 2, start over here so I give myself some space, 2, and then the denominator of 1 plus 4t squared negative 1/2 minus the numerator 2t times the derivative of the denominator, which would be times 1/2, 1 plus 4t squared to the negative 1/2, and then the chain rule times 8t. And then that whole thing is divided by the square of the denominator, so 1 plus 4t squared to the 1/2. Right there is my denominator, and then I square that, so then that would be squared. And there is the second component of the derivative of the unit tangent vector. But let's clean that up because that looks fairly messy. So let's see, so if I combine that, I'm doing a different color to try to help distinguish it on the board here. So let me see, what do we have? The first component here, I've got 8t, negative 1/2, so that's going to be negative 4t on top, divided by, and then I've got 1 plus 4t squared to the 3/2, so 1 plus 4t squared to the 3/2. Second component here, well, so this is going to be 2 times 1 plus 4t squared, negative 1/2. Let me clean this up over here so I can keep it all in the same line. So this was this term here, then I've got a minus 2t times 1/2, that'll leave it minus t, and then I've got 8t, so that'd be negative 8t squared, times 1 plus 4t squared to the negative 1/2. This right here, I'm just going to stare at that for a second. I think that should be positive 1/2. Derivative of the top times the bottom. That should have been a, just for emphasis here, this is what I originally had. Had a minus there, but that should be a positive. Because it's times the denominator, not multiplied by the reciprocal of the denominator. So that should have been a positive 1/2. Okay. So then, let's see, so there's negative 8t squared times that, makes it a positive 1/2 with that correction, and then the whole thing is divided by, let's see, square root, so that will leave me with 1 plus 4t squared. Okay, and then for the let's see. Let's separate the fraction here so I can combine those and combine that. So 4t. And then over here, if I combine those two, that would leave a square root in the bottom. So I've got 2 over square root 1 plus 4t squared. And then over here, that would leave you with minus 8t squared over 1 plus 4t squared. First power, half power, so that'd be the 3/2 power. So that would be the derivative of the unit tangent vector, and now what we need is the magnitude of that. So the magnitude of that, again, do this in a different color here, the magnitude square this, and then add those under a square root. So that would give me, let's see, so square this term. On top I'd have 16t squared. On the bottom, if I square that, that would make that 1 plus 4t squared cubed. Plus, now I'm going to square this. So the, I'd have to remember I'd have to FOIL that. So this is 4 over 1 plus 4t squared. And then the two middle terms would be minus 16t squared over, so it'd be this term times this term. Bases are the same, so you would add the exponents. That would make that 1 plus 4t squared squared. And then we'd have 2 of those, so that would be, rather than 16, that would be, well, let's just write it out. Then the next term would be 16t squared over 1 plus 4t squared squared. And then the last term would be plus 64 t to the 4th over 1 plus 4t squared cubed. And that's all under the square root. So there's the magnitude of the derivative of the unit tangent vector. And then what we have to do to find the curvature formula is I would divide that by the magnitude of the vector v, which would be this right here. So come down here and I would get the curvature is the reciprocal of magnitude of v times the magnitude of the derivative of the unit tangent vector. And so remember, the magnitude of v was given by the square root of 1 plus 4t squared, which means we would distribute that through the whole expression here. And so this would be in the denominator, since this is a square root and this is a square root, I would have 1 plus 4t squared in the denominator, and that's going to get multiplied through all those terms, which would give you each one of those denominators, the exponent would just go up 1. So this would be the square root of 16t squared over 1 plus 4t squared to the 4th plus 4 over 1 plus 4t squared squared. Here there's 32 of those, so I've got minus 32 t squared over 1 plus 4t squared cubed, and then plus 64 t to the 4th over 1 plus 4t squared to the 4th. And I think we are just about done. So there is the formula for the curvature, and remember, we wanted the curvature evaluated at t equals 0. Well, that's going to work out really, really nice, even though that looks messy, because look what happens when I plug 0 in, t equal to 0 into this. This term is 0, this term is 0, this term is 0, this term right here is the only thing that's non-zero, and I plug 0 in, that's going to be 1 plus 4 times 0, which is 1. Then I get 4, so it'd be the square root of 4, which is 2. So therefore, the curvature evaluated at t is equal to 0 is equal to the square root of 4, which is 2. Okay. So there is the curvature of the parabola at the origin. All right, let's go back over here, clean this up, and then let's take a look at finding the equation of that. Here's the sketch of the curve we're looking at. We know that the point that we are using is the vertex here. We know that the curvature is 2. And the theorem that I stated earlier says that the radius of curvature is the reciprocal of the curvature. So that means that the radius is the reciprocal of curvature, which is 1/2. Well, if the radius is 1/2, that means that we know that the point right here has distance 1/2 from this point P. And that means that the center of curvature would be equal to, well, it's on the vertical axis there, so the first component would be 0, and the second component would be 1/2. So 0, 1/2 would be the center of curvature. And remember that the equation of a circle is given by the following. It's x minus a quantity squared plus y minus b quantity squared is r squared, where a and b are the center and r is the radius. So plugging those numbers in, I get x minus 0 squared plus y minus 1/2 squared is equal to 1/2 squared. And then simplifying that slightly, I get x squared plus y minus 1/2 squared is equal to 1/4. So that would be the equation of this circle